For lesson 7.3, day 2, we're going to look at a translation on the t-axis, and in engineering there is something called a Heaviside function. It's a function that's considered on or off, and we define this special function, the Heaviside function, or the unit step function. It's usually written as u of t minus a, and it's thought to be 0 for t between 0 and a. Actually, not even equal to a. Let's fix that. And then 1 if t is greater than or equal to a. And the basic graph that you'd see would look something like this, going from 0 all the way up to some x value of a. We'd be at a y value of 0, and then on 1 from a onward. So as t is less than a and greater than 0, we would be considered off with a value of 0. If t is greater than or equal to a, this would be considered on with a y value of 1. So again, that's the unit step function. Combining the unit step function and a function f of t can turn off or turn on portions of a graph. This is, of course, extremely useful in engineering, especially electrical engineering, and physics situations. Now, for the sake of time on this video, I'm not going to prove the second translation theorem. I am going to send a PDF to students where I'm actually going to show it in class. You could also see it in our textbook. But if we took a Laplace transform, if the Laplace transform of a function f of t is equal to the capital function f of s, and this is for a greater than 0, then the Laplace transform of f of t minus a times the unit step function of t minus a would equal e to the negative as times capital F of s. The proof of this is really just to develop the definition of the Laplace transform, the integration from 0 to infinity of e to the negative st of this integrand inside the Laplace transform, and more or less showing that we'd arrive at this right-hand side of the theorem. But I'd like to very quickly forego the proof and do a quick example. Let's say we've got the Laplace transform of t minus 4 to the 5th power times the unit step function of t minus 4. Now, according to this theorem that we're just seeing up above, what we're going to arrive at is the following. Now, this is also assuming that we know a Laplace transform of a general function f of t. We're going to note here that a would equal 4, and of course our f of t would be t to the 5th, as you can see in this basic setup. So what we'll have is e to the negative as, so that's e to the negative 4s, and then we're going to take the Laplace transform of our f of t. You can see that's really what we're doing. We're ignoring the t minus a for a moment and just applying the Laplace transform of t to the 5th. Well, we've seen what that is before. This is going back to the beginning of our unit. That's going to be 5 factorial all over s to the 6th power. And 5 factorial, by the way, is 120, so we'd get 120 e to the negative 4s all over s to the 6. Now, we could take the Laplace transform of just the unit step function. Now, if you're thinking about that, you might notice that this is very much as if assuming that our function that would be multiplied to the unit step function would be 1. And of course, a constant function, f of t equals 1, so would f of t minus a. Both of them would be synonymous. So what we're seeing really is this. We'd say e to the negative as, just as we did before, times the Laplace transform of just that function of 1. And this would arrive at e to the negative as times 1 over s, arriving at e to the negative as all over s itself. Okay, now if we were to go to the second page, we could very quickly come up with the following graph. Given this graph, let's just say that we're starting off at 3, and this is going to be a constant step of 3 until we get to t equals 2. Then all of a sudden we jump down here to negative 2, and we'll be here until we get up to 3. But then from 3 onward, we'll be on the t-axis. So you might wonder how we could write this function of this graph of this step function, and then how we could apply a Laplace transform. Well, here's how we could do that. Look, we could say f of t, well, what are we starting with? Well, we're starting with a 3. Now, the unit step function generally has a value of 1. But if you look at this, our next step is to decrease from y equals 3 down to y equals negative 2. In other words, we're going to subtract 5. So I'm going to subtract 5 with a unit step function of t minus 2. In other words, this minus 5 is really not going to be applied until we get to t equals 2. It's as if it were off until we got to t equals 2. And that's the beauty of using a unit step function. But then after that, you can see that we immediately rise up 2 additional steps. So we're going to say we'll add a 2, have another unit step function that would go from t minus 3. So at t equals 3, it would be turned on. That's when you'd add a 2. And that would raise our y value up 2 steps. And this would be a great way to represent that function. So real quickly, let's see if we could apply a Laplace transform to this function at hand. So we could apply that to f of t. We could apply it to our constant of 3. Tell you what, how about we just pull that minus 5 out and just apply that Laplace transform to this unit step function here, where a would equal 2, by the way. And then we'd say plus a constant of 2, apply a Laplace transform to u of t minus 3. And by the way, just helping us out a little bit, we could say that a would equal 3 here, a would equal 2. Remember, it's always t minus a. But if we were to refer back to the Laplace transform of a unit step function, look what we just saw a moment ago at the top of the screen. The Laplace transform of a unit step function of t minus a is e to the negative as all over s. So let's see if we could go back and finish this up. A Laplace transform of a constant is always that constant all over s. This would be minus 5 e to, as you see right above here, negative as. That would be negative 2s all over s. And then finally we'd say plus 2 e to the negative 3s all over s, and then we'd be done. So that's our Laplace transform for that function at hand. Okay, there is an alternate form of the second translation formula. We might notice that instead of having a function f of t minus a, sometimes the argument of that function doesn't have a translation. It doesn't have a t minus a in it. But let's say that we're still multiplying to the unit step function u of t minus a. You might wonder what this is going to work out to. Now in class I'm going to prove this. In our book it's proven also. But for right now, let's just copy this down, save some time for our video. Surprisingly, it's going to be e to the opposite as. But now look, we'll be performing our Laplace transform of g of t plus a. And just as a little example as to how that might play out, let's just say that you were given a Laplace transform of a sine of t multiplied to the unit step function of t minus 2 pi. Now notice the very big difference in this problem and what we had begun with earlier in the notes. Now we have the sine of t instead of the sine of a t minus a. And by the way, I hope it's pretty evident in this problem that our a would equal 2 pi. Hope it's also pretty evident that we'd have g of t would equal the sine of t. But according to what we're seeing here, we'd need to find g of t plus 2 pi. G of t plus 2 pi would be the sine of t plus 2 pi. And I hope it's pretty evident that if you saw the sine of t plus 2 pi, think about it this way, just from basic unit circle trig. If you had t plus 2 pi would always be coterminal with t. This would be synonymous with the sine of t. Now we could use the sine sum formula and show that and prove that, but that wouldn't even be necessary. Let's follow this through very quickly. According to this second translation theorem, this should be e to the negative as, so that would be e to the negative 2 pi s. And then we're going to have the Laplace transform of the sine of t. Well, what exactly is the Laplace transform of the sine of t? Well, hopefully we remember that quite well. That's going to be with a k value of 1 here. It's k, which is 1, all over s squared plus k squared. Well, k squared's just your 1 squared. And just combining some terms here, we'd get e to the negative 2 pi s all over s squared plus 1. So this would be a second translation theorem. We would use this if our function doesn't have that horizontal shift, if it just has g of t. Okay, this last part of the lesson, the inverse form of the second translation theorem, is going back to our first form of the translation theorem. We're just going to work it backwards. And you can see what's happening. We're effectively going to say, rather than starting at A and ending at B, what if we start at B and then go backwards to A? So that's really what our goal is. What if we were to say the inverse of E of opposite AS of capital F of S? Well, that should equal f of t minus a times the unit step function of t minus a. We're going to pick up with one final example in just a moment.